The periodic table, as it's normally laid out, really is a fantastic cheat sheet. There's so much information packed into this thing. We can look at chemical properties, bonding, states of matter, and one of the things that we usually want to know is the ground state electron configuration. Because as much as the nucleus plays a role in how the chemical is going to behave, chemistry really involves the outermost electron shell, or the valence electrons, and how those interact with the other electrons and other nuclei. Okay, to make it a bit easier on ourselves to find the ground state electron configuration for each element, first we're going to move around a few things. So let's move helium over beside hydrogen, and that puts it in line with the other elements whose outermost electrons are in the s block. Next, we're going to expand the space between these s orbital elements and the d block to make room for the f block elements. Now that we have the table laid out this way, it's a little easier to see which elements have which orbitals as their outermost electrons. So first we have this blue column, the s block, or the ones that have the outermost electrons in the s orbitals. Then we can move over to the p orbital block, then the d block, and finally lowest down the f block. And we can also number the rows accordingly. So s orbitals start at principal quantum number 1, so we start counting at 1, 2, 3, 4, 5, 6, 7. And we can do the same thing for the p orbitals. So they start at principal quantum number 2, so we go 2, 3, 4, 5, 6, 7. The d block begins at n equals 3, so we go 3, 4, 5, 6. And f starts at 4, so we only have 4 and 5. Okay, so now there's really nothing left to do but count if we want to know the electronic state for any of these elements. So why don't we target gold? It's far enough down that we're going to hit every block. So there's gold. And it's got 79 protons in its nucleus. So we know that we need 79 electrons to make up the balance for a neutral atom. So how are we going to arrange those 79 electrons? So first, we have to count up the orbitals and the principal quantum numbers starting at the lowest possible numbers. So that's first the 1s orbital, and we can put 1, 2 electrons in that 1s orbital. So we put a superscript 2 just to show that we have 2 electrons in the 1s orbital. Okay, so that's 1 and 2. Next we hit 3 with lithium, and that's in the 2s orbital. So we have 2s, and again with s orbitals we can only fit 2 electrons in it, so it's full with 2, because we're still counting up towards 79. So that's 4 so far. Next we have to jump over to the p block. So next we have 2p, and there's going to be, remember there are 3 p orbitals and 2 electrons in each, so that's 1, 2, 3, 4, 5, 6. And it's full for gold, so we're going to write a 6 in the superscript. And we continue on like that. So we have 3s2, and then 3p6, 3p6. Okay. Okay, and then the next one we run into isn't 3d at scandium, but the next one we're going to run into is 4s at potassium. So that's the next one we write, 4s2, then 3d, and we haven't said it yet, but there are 5d orbitals, each with 2 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, it's full on our way to gold, so we have 3d10. And then following that 3d10 electron, we go into the 4p electrons. So 4p, and again, it's filled with 6. And then we move on to 5s2, 4d10, 5p6, and then 6s2, and now we finally reach our F block electrons. So they start at 4f. We can't have anything smaller than 4f, so we're starting at 4f. And there are 7 f orbitals, so that means there are 14 f electrons, or f block electrons, on our way up towards gold. So that's going to be filled at 14. And now finally we're in the block, in the row that holds gold, so now we have to really count them up in this 5d electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is 5d9. And that is the electron configuration for gold. So these are the numbers of orbitals, the types of orbitals, and the numbers of electrons in each of those orbitals in any gold atom, any neutral gold atom. What else can we say about that? We can simplify it quite a bit, shortening it by just saying that all of the core electrons, or the ones that don't really participate in chemistry, are locked away inside the equivalent xenon electron configuration inside the core of a gold atom. So we can show that by writing square brackets around the xenon chemical symbol, and then only writing up the valence electrons on top of those. So that's everything greater than the 5p6 completed fifth shell. Okay, so that is the 6s2, 4f14, and 5d9. Okay, so this is just a shortened version of the same thing. So here we say we're indicating which are the core electrons. So core, that again don't participate in any kind of chemistry, and our valence electrons, which do. So next door to gold, we have mercury, which, as you probably know, is kind of an interesting element just because it's the only metal that's also a liquid at room temperature. Have you wondered why that is? Part of the reason is that it has a completed suite of d electrons. You'll see that it gets up to 5d10, completes the block, and it's quite satisfied in that. But why aren't zinc and cadmium also liquid if it's the electron configuration that makes the difference? So the electron configuration can answer plenty of questions about the chemistry and behavior of the elements, but to know the answer to that, we have to dig a little deeper, and we'll do that next time.